Today's lesson, we are looking at three-phase systems and there are two types, star and delta connections. First, we are going to draw a star connection. A star connection has three common ends of each phase connected to a common endpoint called the neutral point. A star connection is also called a Y or Vi connection. What is the purpose of the N? For unbalanced loads, the unbalanced current will flow in the neutral wire. Line voltages are √3 more than the phase voltage. What are the uses for star connections? Star connections are used for transmission lines to allow a small current to flow through smaller conductors and minimize the copper losses or the I²R losses. The N is the neutral point used for unbalanced loads. So this is a 4-wire system if it includes the N. If it does not include the N, it will be a 3-wire system. Next, we are going to draw the phase and line voltages. Explain what is meant by phase voltage. So the phase voltages are between the neutral and the colors red, yellow and blue. So the first phase will be red and neutral, second one will be yellow and neutral, and the third one blue and neutral. We're now going to draw loads between between the phase voltages. Red and neutral, yellow and neutral, blue and neutral. We are now going to draw the line voltages between red and yellow, between yellow and blue, and between red and blue. What will the voltage between red and blue if the voltage between blue and neutral is 220 volts? So all we have to do is calculate the phase voltage. So V line is equal to √3 times V phase. Substitute our values, the phase voltage being 220, and we get a final answer of 381 volts will be the line voltage. Before we go to delta connection, we'd like to explain the properties of star. In star, the phase current is equal to the line current. That is, IL is equal to I phase. The line voltage are 120 degrees in time apart from each other. The line voltage is equal to √3 times the phase voltage, that is, line voltage are 1.73 times greater than the phase voltages. The line voltage leads the phase voltage by 30 degrees, and we're going to draw a diagram to explain that. Don't forget that the direction of rotation is anti-clockwise. The three lines must be drawn 120 degrees apart. That is the line voltages. So even with generators, the stator windings are 120 degrees apart from each other, and this produces the magnetic rotating flux in a generator. So here we have VBR, VRY and VYB. These are 120 apart, and these are your line voltages. Notice the direction of rotation, and it says that it's going to lead by 30. So VBN will be 30 degrees lagging VBR. So VBN is lagging 30 degrees VBR. VRN will lag 30 degrees VRY. And VYN will lag 30 degrees VYB. Between VBR and VRY, as the notes read above, there are 120 degrees apart. Between VBR and VYB, they are also 120 degrees apart. Between VRY and VYB, they are 120 degrees apart. So 360 divided by 3 will give us that 120. And each red phase voltage will lag the line voltage by 30 degrees. Next, we're going to draw a delta connection. Each of the ends of each phase are connected in series to form a closed loop. This is called a mesh or a delta system. V phase is equal to VL, but the line current is root 3 times greater than phase current. So we are going to connect loads between R and Y and B, R and B. Line currents are displaced 120 degrees apart in time. And now R and B. Line currents lead the phase current by 30 degrees. Line current is root 3 greater than the phase current. And root 3 times I phase is equal to I line. I line over root 3 is equal to I phase. The use. Large amounts of three-phase power is needed in big companies. So it's used where higher currents are required. Next, we're looking at the advantage of three-phase over single-phase. So we're comparing advantages and advantages. So three-phase has worldwide adoption, generation, and distribution. Single-phase can be sought from three-phase. Power supply is constant with three-phase. And with the single phase, it's used in residential applications, households, schools, and small buildings. With the three phase, it is more economical and it uses less copper due to the thinner conductors. So because it's more economical, the conductors will be thinner, carrying less current in them. Single phase is used by smaller, cheaper appliances. The three phase balancing loads can be done, and single phase appliances are cheaper. Other things to consider with a three phase is that there's a 4-wire system where it makes use of a neutral point, and a neutral point is available in star. And the neutral point is what's used for the balancing of loads. Also, with three-phase, we can get star and delta connections, and two voltages can be obtained from a star connection. Disadvantages. Three-phase installation costs are high. So disadvantages of three-phase and single-phase disadvantages. Installation costs are high, cannot be distributed economically over long distances. Disadvantage of three-phase, not available locally everywhere in your local community. Not everywhere they'll have three-phase. With the single-phase, larger currents, thicker wires, thicker conductors needed. Disadvantages of a three-phase: appliances are expensive. The single-phase, for equivalent machine or application, it is not as economical as a three-phase system. So if we have motors of the same size, we'll find that the three-phase motor will be more powerful. Okay, next we're looking at a schematic diagram. Please note, for schematic diagrams you must label them. Start off with your delta and your star. Label the neutral point and label all the corners of the points as so. Next we're looking at the advantages of power factor improvement. Don't forget that power factor is cos theta. Number 1, reduces current in supply conductors. If you're getting full power, then surely your conductors will be thinner. So number 2, smaller supply conductors are required because you have a lesser current running through these conductors. We can now use smaller supply conductors. Number 3, reduces the monthly electricity bill because now we've got less losses. Number 4, less maintenance is required on the equipment, and if we got less maintenance on the equipment, then surely, number 5, our equipment will last longer. If our equipment lasts longer, then we are saving money. So we save money also on our equipment, and we save money on the supply conductors being smaller. So less copper means a saving in price in terms of buying the copper. Right, and that's the advantages of power factor improvement. Right, the next question we're looking at. A three-phase system has a delta star connection. The primary line voltage is 380 volts. So VL1 is equal to 380 volts. We can label that on the diagram. And VL2, the primary side, VL2, the secondary side, is 220 volts. So the first part of the question says calculate the phase voltage when connected in delta. So VL is equal to V phase for delta connections on the primary side. And that's going to equal to 380 volts. For second part of the question, calculate the phase voltage when connected in star. So V phase is equal to VL2 over root 3. So that is the secondary side. 220 divided by root 3. Our answer, final answer is 127.02 volts. Okay, the next question says a 3 volt star connected load is supplied by a 50 kilovolt amp generator at a current of 40 amps. The power factor of the load is 0.86 lagging. Calculate the following, the active power. So you can use the formula P is equal to VI cos theta, but it doesn't look too realistic. So we're going to use the one we normally do for 3-phase. So 3-phase, root 3 VLIL cos theta. Now we're going to substitute our power for all that's in brackets. So that will be 50,000. Don't forget cos theta is 0.86. Cos theta is power factor. Plug it into our calculator. We're going to get power is equal to 43,000 volt amps. We can convert that to 43 kilovolt amps. But what would be better is power is equal to 43 kilowatts. Alright, the next question. A three-phase delta connected load is supplied by a 200 kilovolt amp generator with a phase voltage of 380 volts. The power factor of the load is given as 0,9 lagging. They want us to calculate the line voltage. So we can start off with the formula. S is equal to root 3 VLIL cos theta. Some of these questions you find they calculate the IL and they do not take the power factor into consideration, especially when it's in a delta connection. But if you had to include the power factor, they will still give you the full marks, as I've noted in some other questions. So if they put the power factor there, I would say use it. So our formula there we'll use is root 3 VLIL cos theta. Our line voltage is 380. And our power factor is 0,9. We do not have I. We will need to calculate our phase voltage. So they tell us the phase voltage is 380, but our phase voltage and our line voltage is the same. So we will get 380 because it's a delta connection. So we substitute our 220,000 and manipulate the formula, substitute, we get the final answer, 337,63 amps. For something like this, it will be 4 marks in the exam. The next question, a three-phase system draws 5 amps at 220 volts and outputs 10 amps at 50 volts. Determine the efficiency of the system. So efficiency is output over input times 100%. So first we're going to calculate our primary input. Then we're going to calculate our secondary output. Efficiency is output over input times 100%. Our output is calculated above, we'll substitute it. And our input calculated above, we'll substitute and get a final answer. 45,45%. The next question is also an AC generation. A 380 volt three-phase system is star connected to a lagging load. Input power is 25 kilowatts. The load causes a power factor of 0,9. Given we have VL equals 380V, power in is 25 kilowatts, and cos theta, which is the power factor, 0,9. The first question is to calculate the phase voltage. So V phase is equal to VL over root 3, 1 mark for the formula. Substitute our value of 380 for the line voltage divided by root 3, and our final answer is 219,37 volts. For a question like that, we'll get 3 marks. The next question is the line current to the load. Power is equal to root 3 VLIL cos theta. We need to make IL subject to the formula. You get 1 mark. Substitute 25,000 for power, and VL is equal to 380. Do not mix it up with the phase voltage calculated above. VL is 380. Substitute that. Final answer, IL is 42,2 amps. The next question says the reactive power, and the reactive power is Q. The formula there is Q is equal to root 3 VL IL sine theta. 1 mark for the formula. Our VL is still 380. Our IL we calculated above. And don't forget, we need to find out what is the phase angle. The phase angle is 25,84 degrees. So we will substitute sine 25,84. Our final answer, Q is equal to 27,775,17 VAR, reactive. So we can simplify that to Q is equal to 27,75 kilo VAR. A question like this will be about 3 marks, maybe 4 marks.